Decibel is a relationship between physical variables, particularly acoustic or electric power, and to quantify the relative loudness of sounds. One experiment is carried out to see if an automobile with different RPM would have a long-term effect on human health. Five types of car will be used in this experiment. There are three objectives for this project. First, to be introduced to the process of capturing and measuring engine sound signals of different engines at different revolutions per minute, and understand how digital signal processing is achieved. Second, to compare and analyze the characteristics of the engine sound signals of five different model cars obtained for varying input parameters in Audacity and MATLAB application. Third, to analyze which car engine sounds contribute to noise pollution.
For literature review, negative impact from noise pollution has been well identified by doing research. As in terms of transportation, sound of an engine is classified as one of the pollution sources, including from its revolutions per minute RPM, such as measured in our project. Based on the NIOSH, the safe sound level for humans' hearing system is in range from 40 to 45 decibel. At 85 decibel, it is still safe within 8 hours of listening without protection, and it is the maximum safe value. However, the WHO states that exposure to noise level exceeding 70 decibel may cause hearing loss, sleep disturbances, and even cardiovascular disease. As a result, automotive engines that generate noise exceeding 70 decibel could be categorized harmful to public health generally. How do we analyze this sound wave? It could be done using fast Fourier transform or FFT technique, such as written in article by Alan V. Oppenheim, where we could extract the frequency details from the sound wave. Millions of engineers and scientists utilize it as a programming and numerical computing platform to analyze data, develop algorithms, and even build models.
As for the methodology, an engine of Honda Civic was recorded using a smartphone at idle state for 7 seconds. Then change the RPM to 1500 RPM, 2500 RPM, and lastly 3500 RPM. After collected the data, change to the other cars such as Pro 2 Myvi, Toyota Vios, Pro 2 Cancel, and Proton Gen 2. And then convert all the audio to the Audacity software and import to the MATLAB to generate the graph.
For the design concept, it aims to reduce the speed of engine car, reduce the noise level, and optimize the overall performance of car. The design concept focuses on identifying the type of car that produces high noise level. When the speed of the car is increased, it will result in higher sound intensity. The intensity of the sound is compared based on spectrum analysis, data that is obtained from various types of engine cars such as Pro 2 Cancel, Pro 2 Myvi, Proton Gen 2, Toyota Vios, and Honda Civic. A few other ways were taken to lessen the presence of background noise. In the process of collecting the data, the choice of venue is based on the quietness of the place. This is to reduce any errors that could occur during the process of recording audio of the engine car.
For the result, we utilize Audacity software to perform spectrum analysis from the recording of 5 different car engines to identify the peak sound level of each car engine at idle state and 3500 RPM. We also create chart to compare the sound level obtained from this recording. Next, we export the data from Audacity software and process it by using MATLAB. Through various coding techniques, we generated graph representing the frequency domain and time domain for each selected car engine. Finally, we also use MATLAB to produce a graph illustrating the sound level pressure of each car engine, aiming for simple yet effective representation.
The spectrum graph in Audacity provides a visual representation of the frequency characteristic in recorded audio, showing the energy distribution across different frequencies. By analyzing the spectrum graph, we can determine the engine sound level of different cars at ideal and 3500 RPM. peaks in the spectrum graph indicate frequencies with higher energy or louder component, while valleys represent frequencies with lower energy or quieter component. Gen 2 had the highest engine sound level and louder component at idle, while Civic had the highest peak engine sound and louder component at 3500. The time domain graph shows changes in the engine sound waveform over time with increased amplitude fluctuation as RPM increases. The engine sound signal of Civic at 3.5K RPM appears to be highly intense compared to other models as indicated by its taller waveform. The frequency domain graph reveals the presence of prominent peaks and spikes, indicating frequencies with highest intensity or energy in the signal. The graph for Civic at 3.5K RPM exhibits the most prominent peaks and a concentrated energy band within a narrow range of frequency. The SPL graph illustrates sound intensity or loudness across different frequencies, showing the magnitude or intensity of sound at each frequency. Variance in engine speed correlate with differences in sound loudness, with high RPM level generally resulting in higher sound level. Inaccuracies in the recorded engine sound level may be due to limitation in recording equipment, environmental factors, errors in data collection, calibration issues, or human error. It's crucial to address these potential errors and ensure the reliability of the data for accurate analysis.
The process of capturing and measuring engine sound signals of different engines was achieved. The characteristic of the engine sound signal was compared and analyzed from spectrum, time domain, and frequency domain graph for 5 different cars. As per data, the engine sound level of the Gen 2 was the highest at idle RPM, while the Honda Civic had the highest peak engine sound level at 3,500 RPM. The Civic, expected to have a quieter engine sound at higher RPMs, had the loudest sound according to the data. Further investigations with improved recording techniques, control environments, and careful data handling are necessary to draw more definitive conclusions about noise pollution and sound quality.